This video corresponds with Chapter 10 in your textbook, the Paired Samples t-test chapter. You'll notice that I've called it the Dependent Sample t-test, which is another way of talking about a paired samples t-test. So this particular example, we talk about whether or not a small gift improves students' mood during statistics class. So here's the study. 8 statistics students were given a small gift of candy to see whether it would influence how they rate their mood. At the end of a 4-hour class period, students were asked to rate their mood on the following scale, from 1 being not at all positive to 7 being very positive. As you can imagine, at the end of a 4-hour statistics class, most students weren't rating their moods as being particularly positive at all. So they were then given a chocolate bar and asked to rate their mood again on the same scale. So what we want to test is whether or not that candy gift significantly changed their mood. Did it significantly influence them to rate their mood more positively? So again, we start with our population, comparison distribution, and assumptions. So with the populations, we're talking about student moods before we give them a gift of candy and after we give them a gift of candy. Again, this is a within subjects design, and so everybody gets or has a score from before some kind of intervention, and then they also have it from after some kind of intervention, in this case, the gift. And you'll also notice that this is what's typically referred to as a pretest, post-test design. So that's our population. Our comparison distribution is a little bit different now, and I'll give you a little bit more information about that as we go through the calculations. The distribution is a distribution of mean differences. So it's the average of a set of different scores. Oops. Again, we are still talking about a distribution of means, or actually a distribution of mean differences, but it's similar to that distribution of means that we've been talking about. And it is less spread out than the distribution of scores. So we have to have some sort of comparable measure of standard error. Next we have our assumptions. And again, the assumptions are the same as what we've seen for the z-test and the one sample t-test. So the first is that the distribution is approximately normal. And again, we can be pretty well assured that that's going to be the case if we have at least 30 students. So we need to be a little bit cautious here about whether or not this is a set of normally distributed data because we only have 8 students. The second, again, is random selection. Now we know that these weren't randomly selected. These were a convenient sample, and so we have to be careful about our generalizability. Maybe there was something about this particular group of students that made them much more susceptible to influence of the mood. And the last is the dependent variable is scale. So this is a rating that students give about their mood, and so yes, it is a scale variable. So now we need to state the null and the research hypotheses. And we are working with a two-tailed test in this case. So students' moods are unchanged by the gift of candy is our null hypothesis. We could also note that symbolically by saying the mean of population 1, or the mean of before, is equivalent to the mean of after. And we could say our research hypothesis is that students' moods are different after receiving the gift of candy. And we could say then that our research hypothesis symbolically is that the mean of before is different, not the same as, not equal to, the mean of after. So now we need to find the characteristics of the comparison distribution. And from step 1, we know that the comparison distribution is a distribution of mean differences. Remember that I said that I was going to explain a little bit more about what I mean by this distribution of mean differences when we get to step 3. So we need to find out what those characteristics of our distribution of mean differences is. And you'll notice that we now have m subdifference, a mu subdifference, which refers to the difference that we find within our own sample. And then we have a hypothesized mu subdifference. And we also have an estimated standard error, because again, we're still working with a t-test, and our population standard deviation is unknown, and we need to estimate it based on our sample information. So here's how we would go about calculating our difference scores, because essentially what we're doing is a one sample t-test of difference scores. And this is what I mean. Notice that we have a column of mood ratings before, and we have a column of mood ratings after. So you can see that the scores are a little bit lower before, and they're a little bit higher after. But what's really important here is that each individual, we have their two scores, and so we can see what that change in mood looks like. So the first step in this process is to calculate the difference scores. So I took after and I subtracted before because I was really thinking that they would probably improve in mood. And so if that's the case, then we would expect our after scores to be higher and those difference scores to be positive. So for each pair, I took after, subtracted before, and recorded the difference over here. And then after that, we don't need the first two columns anymore. You can just cross them off, scribble them out. We don't need them because now we're working with this set of difference scores. And it's just like the one sample t-test that we've been doing. So we find the average of these difference scores, and if we add these all together and divide by 8, we find that we get an average difference of 2. So that's an average improvement of 2 points on this set of scores. So we can take this score then and we can subtract it from each difference score. So this is analogous to doing our estimate of the standard error, or standard deviation, which will then get to the standard error. So if we took each of these scores and subtracted out 2, then we would get this set of scores. And then we go ahead and square those to get our squared deviations. And if we added all of these squared deviations together, we could get our sums of squares, which we would substitute here for the top part. And again, we have this correction on the bottom where we take our number of difference scores. Okay, so we have 8 pairs of scores, so it will be 8 minus. So here we have in the denominator 7, and in the numerator it's the sum of these squared deviations, which is 12. We get 1.71, and we need to take the square root. So our estimated population standard deviation is 1.31. So now we can come back here to fill in these characteristics. We learned from our computations that the mean of the difference scores is 2. And we also learned that our standard error that we estimate is based on the standard deviation divided by the square root of n. And that gives us 0.46 because we substituted in that standard deviation and we took the square root of 8. Now remember here that again this is the number of pairs of scores that you have, or the number of different scores that you have. And you don't use n minus 1 to calculate the standard error. That leaves us with this last piece of information here, the mu subdifference, for the mean of the distribution of mean differences. So essentially, if we imagine that our null hypothesis is true, then the difference between before and after at the population level should be 0. So this mu subdifference is 0, and the mean of those differences is 2. So now we have all of our characteristics here. And generally speaking, this mu, the difference at the population level, is going to be 0 almost always for the paired samples t-test. And that's because we are hypothesizing a null difference between the two. Okay. So that brings us to step 4, where we determine the critical values. What are our cutoffs? And again, because this is a two-tailed test, we have our research hypothesis that they're not equal. We set alpha to be 0.05, which is our type 1 error rate. It's a two-tailed test. So we need to calculate our degrees of freedom, which is going to be based on n minus 1. So the number of pairs of scores. Remember, this is something that usually throws people off. It's the number of pairs of scores, not the number of scores for both variables added together. So here we have 8 minus 1, so we have 7 degrees of freedom. Remember, degrees of freedom are how many different values are free to vary after, say, you're calculating a mean, and you know that the mean has to be 5, and you have 10 people in your sample. You get to the 10th person, whatever their score is, in order to make that mean be 5, is fixed. So it's not free to vary. So that's what the degrees of freedom get at. So that brings us to finding the critical t. So if we go into the back of our textbook, table B2 shows us the t distributions. And this is just an excerpt of that. But if you come down here, we know that our degrees of freedom is 7, so you find that in the first column. And we also know that we've set our type 1 error rate at alpha equals 0.05. So here we have our critical value, where those two intersect, of 2.365. And it's actually plus or minus 2.365, because this is a two-tailed test. So we can mark that. Then on our distribution, we can draw this in. 2.365 above the mean, and then below the mean, negative 2.365. Those are our critical values. If our score is beyond, our t that we calculate is beyond 2.365, we can reject the null hypothesis. Same if we have it greater than negative 2.365, or more extreme than negative 2.365. And again, that's because we put that 2.5% in each tail. So let's calculate our test statistic. We'll start by finding our givens. The first is that the mean of the distribution of mean differences is 0. The second is that standard error of the mean that we've estimated, which is 0.46. We calculated that in part 3. And here we have the number of scores, and this is our population mean. So now we can do our computation. So we have the mean of our different scores, and we subtract out the mean of the population of different scores and divide by the standard error. So we have 2 minus 0 divided by 0.46, and we get a z-score of 4.35. So if we come back here, we have that z-score of 4.35. It's going to fall out here. It's extreme. And because it falls beyond those cutoff scores, then we get to make the decision to reject the null hypothesis. So there is a significant difference in student mood after receiving a gift of candy. So we could say students rated their mood as being significantly more positive after receiving a gift of candy. And here that's the mean that I calculated for the before scores, or I'm sorry, for the after scores, which is a score of 4, which is a little bit above neutral. So it's not extremely positive, but on that 7-point scale, it's better than just being kind of neutral. It did make them a little bit happier than they did before receiving the candy. So before receiving the candy, they were kind of a not very positive mood, too. So, and you also see in APA style, we have that t-test, our 7 degrees of freedom equals 4.35, that's our t statistic, and the probability is less than 0.05. So when is that dependent sample t-test used? Well, we use it when we have a within subjects design, meaning that every participant gets all levels of the independent variable, and we are comparing two different means.